Okay. So today onwards we'll start on turbulence modeling, and let's see how this will probably, what we had done till now, we looked at the turbulent flow equations for various flows, especially the shear flows, and for the boundaryless flows like the jets, wakes, and mixing layers, we looked at the self-similar solutions. There's a homework due tomorrow, I'm sure. Probably it's not very difficult. You should be able to get it. And then I'll give you one more homework in a day or two, which will probably some things based on this. I hope are all of you comfortable finding the eigenvalues, eigenvectors, etc. of anything. So I'll give you something based on what we are doing now. So either tomorrow or on Friday. We have 1 week, so I think we should be able to take care of that. So now and we'll start off with the mean momentum equations. This equation we have already derived in the homework also and in the class also. So I'll just write it. All of you are familiar with this equation. Okay, I don't need to tell you this is the mean momentum equation obtained by averaging the Navier-Stokes equations. Okay, in fact, we have gone one level further, and then in addition, we also have the continuity equation for mean flow. And there are some terms which we have done, so I'll just write the mean of capital Sij. We wrote it as half of this is the rate of strain tensor, the mean rate of strain, and this is the mean rate of rotation tensor. Again, this has been done. One is the symmetric part, one is the antisymmetric part. And also what we have is, we know partial mean Sij by partial xj. This is equal to half d2 of mean of ui. And here in writing this continuity equation has been used. So therefore, we have this term in the momentum equation. So either we can write it like this or we can use the partial Sij by partial xj. So we can use one of these two, and this is what the equation is. Now, if I look at the mean equation, the right hand side of the mean velocity equation, this is partial by partial xj of mu times Sorry, this bracket should have been. This was this bracket minus we have P times the right hand side of the mean velocity equation had three terms. So this term was d2 ui by dxj, which with invoking the continuity equation becomes mu times 2 mu times sij. The 2 and the half cut out each other. And then we have, it was partial p by partial xi. So that can be written as p times delta ij d by dxj. Because then when you operate d by dxj, then this will go away and we'll get partial p by partial xi. And similarly, this rho u prime, we had it in the same. Now, the reason we write it like this is all the three terms on the right hand side, at least two of them we are very familiar. This is the viscous stress term, and this one is the pressure or the isotropic stress, and this term which comes because of averaging of the equation, this is what we call as the apparent stress, and there are different names we have given to this. Reynolds stress, this is what we have. So now, firstly, I will take some pains to explain why this behaves like a stress. Okay, this is a velocity correlation. Why do we call it a stress? But before that, when I try to look at this set of equations, what is a closed set and what is an unclosed set of equations? The number of dependent variables is equal to the number of equations. Okay, so a closed set will be now. Hello, hello, hello. I think it was by error. It was gone from an embassy, so I had to take it. Okay, so a closed set. Now here, if we look at this, this is the equation for mean of ui. Mean of ui will be three terms, three scalars, and then there is a mean pressure. So that means totally we have four terms, but let's forget this. I'll come to this in a moment. So there are four terms and these are the four equations. But then there's a term here ui prime, uj prime, for which there is no equation. If I look at just these two equations by themselves, then I find ui prime, uj prime is equationless. Okay, and this is what we say is the closure problem, that the equations are unclosed. The mean velocity equations, and this will always happen if you have a non-linear term. This term is coming from the non-linear term. All the linear terms have changed in the same form in the averaged equation. When you average out all the linear terms, you get the same form. You get this term, you get this term, you get this term. But the non-linear term leads to something like a product of fluctuations, which is not zero. And that is what leads to the closure problem. Okay. Now, this is the closure problem for the mean flow. Now, someone can say that let's write the equation for ui prime, uj prime. When we do that, we'll find, and as we know, higher order terms come. And so the equation will never get closed by taking the mean. And this is what we call as the closure problem of turbulence. And what is the meaning of turbulence modeling? That if we are to solve this set of equations, if we were to solve the instantaneous equations, are they closed or unclosed? They are closed. They are 4 variables, 4 equations. If we are to solve them, if we can solve them, we would have solved them. But we cannot solve them, so we go to the mean, and because we feel the means will be at a bigger scale, so we can solve them, but then we encounter the closure when we take the mean. And so now to express this, how do we resolve the closure problem? By writing this as a function of one of the other variables. Writing this as a function of mean p, mean u, or other constants which are there. If we are able to do that, that is what we call as modeling of turbulence. Modeling this or modeling the unclosed terms. And what do we mean by modeling? Expressing them in some reasonably rational and scientific way. Writing them as a function of the variables for which you are solving. You still don't know the mean velocity. But if I express this as a function of mean velocity, then a mean velocity will come in the equation. So when I solve the equation for mean velocity, automatically this term will get known. It doesn't mean that you have to write it fully. You write it in terms of other variables, but you will be solving the equation for those variables. So that is what the closure problem is, and that is what turbulence modeling is. So let me just write this down before I talk of the closure problem. That we have equation for mean ui and p, or sufficient equations for mean ui and p, but no equation for ui prime uj prime. So ui prime, this is what we call as the unclosed term, and we resolve it by modeling express also think of writing equations for ui prime ej prime uj prime. Equations for So all what I have said, I have written here, and I have explained what is the closure problem. See, because often you may encounter some of your master students when you come for PhD interview, we may ask you what is the closure problem of turbulence. So then you say that we try to close by writing the second order equation. Well, first we write the equation for mean contains ui prime uj prime. We write the equation for ui prime uj prime. It contains even higher order terms, and this doesn't end, and so that is the closure problem. And the remedy, or how do we try to attempt the closure problem? By trying to write modeling approximations or turbulence modeling. And that is if you are not solving the full equations. The equations, once again I emphasize, the equation for ui, for instantaneous u and p is closed. Those equations are closed. It is not that they are unclosed, but we cannot solve those equations even numerically. So that is why then we have to go for this. If you try to solve the full equations, that is called DNS, direct numerical simulations, and which now slowly as computers are advancing, we are going up to more and more level of Reynolds number for which you can solve those equations. We'll look to see if we can give you a bit of a flavor of DNS maybe in the last lecture. But now here, let me explain the physics of some physical interpretation of the stress terms. The viscous stress, which is the term containing mu, the viscous stress, which is force per unit area, arises from the momentum transfer at molecular level. Whereas the Reynolds stress, now once again in Reynolds stress, actually if you call it as a stress, then Reynolds stress should be rho times ui prime uj prime, because the dimensions only then will match the dimensions of stress. But often we write only ui prime uj prime as Reynolds stress, because in incompressible flows, if rho is constant, it doesn't matter. So therefore, you will see actually we use more ui prime uj prime as Reynolds stress. My Hello, I'm in a class. I will call you back. हाँ, मैं क्लास में हूँ, मैं आपसे बात कर लूँगा, थोड़ी देर में बात करूँ. Now, असल में my phone got stolen on before Diwali, so I'm using my old phone with I've forgotten most of it, so the volume is very loud and actually it's probably इसके बाद तो मैं वही कर देता हूँ ना अभी, getting a bit too much for the class. Okay, now it will syllabus. So now Reynolds stress arise from momentum transfer by fluctuating velocity field. The fluctuating velocity field, as the terms ui prime, uj prime, as the particle moves, it carries some momentum along with it. So that transfer, which comes from the ui prime type of terms, is what is reflected in the Reynolds stress. And if we, let's say, if there is a volume V, and this volume V is bounded by an area A. So area A is the binding area, and at any point N is the outward normal. Okay. So the rate of gain of momentum in a fixed control volume V due to flow through surface A is given by the rate of gain of momentum. This is equal to let's try to explain that momentum per unit volume is equal to the vector rho u. We are talking of rate of gain of momentum due to flow through a surface area A. So we've calculated over each part of the area. So first I'm calculating the integrand. Now momentum per unit volume will be rho u. And how much is the inflow of volume through this area dA? That is equal to u dot n dA. U dot n will be the outflow. So I put a minus sign, that will be the inflow, because n is always pointing outwards. So this minus u dot n dA gives us the minus u dot n dA. This is the rate of flow which is coming in, and rho u is its momentum. So the total rate of change of momentum which is coming in the volume will, because of this flow, will be momentum per unit volume multiplied by the volume which is coming in per unit rate of volume. Okay. So that's what I'm trying to express in momentum per unit volume is rho u, and volume flow rate per unit area, so that means we'll not multiply by dA, into V through area A is minus u dotted with it. So the ith component of this flux will be ith component of average momentum flux will be, I take the average of m dot, and when I take the average, this is where you will see, when I take the average, there is a u times u. So this will give me u and u average and plus average of ui prime, uj prime. And then there are two more terms, but they will become zero, because when you take the average, there's the average times fluctuation and the average of that. So they're the same thing. So therefore, when I take the average of this, what I will get is m dot I will be equal to integral over the area minus rho mean of ui uj plus ui prime uj prime nj multiplied by d. So that is why we get these two terms, and then this will become equal to the volume integral of minus rho d by dxj of ui uj plus ui prime uj prime dv. So for the control volume V, Reynolds stress as it appears in the mean flow equation which is minus rho times d by dxj of ui prime uj prime arises from mean momentum flux due to fluctuating velocity on the क्या हो रहा है इसको on the boundary A. Sorry. So basically the mean momentum flux comes like this. Now we have already seen the closure problem. Let us look at the tensor properties of ui prime uj prime. So firstly we realized ui prime uj prime is a second order tensor. Okay, there are two free indices. This is a second order tensor. Not only this, we also realize this is a symmetric tensor because ui prime uj prime will also be equal to uj prime ui prime. So therefore, this is not only is it a tensor, it's also a symmetric tensor. Then we look at its, so this tensor looks like u1 prime square, u1 prime u2 prime, u1 prime u3 prime, u1 prime u2 prime, so this is how this tensor looks like. It is symmetric, so there are totally 6 independent components. Now, the diagonal components which is u1 prime square, u2 prime square, u3 prime square, these are the normal stresses, and the off diagonal terms these are the shear stress terms. Now also we know we have introduced turbulent kinetic energy K, and K is equal to half of ui prime ui prime. And this K is the mean kinetic energy per unit mass of the fluctuating velocity field. We have already seen what K is in the flow. Now, whenever we have a second order symmetric matrix, then it turns out that we can express, if we express it in its principal components, then the eigenvalues have to be positive or zero. They cannot be negative if it is a symmetric matrix. That is a well-known this thing. So, what one can do is, if in principal axis of Reynolds stress, so if we rotate the Reynolds stress tensor along the principal axis, shear stresses will be along the principal axis. What will be the values of the shear stress? अगर हमने तो zero होंगी principal axis में, if we rotate, then the values of shear stress will be 0, and the normal stresses in the principal stress are nothing but the eigenvalues. And these eigenvalues are non-negative. Now, let us look at another term. We have already seen some of it. Let's look at the Ni. We have seen this before, that any second order tensor, whether it is symmetric or asymmetric, we can divide it into two parts, isotropic and a deviatoric part. The isotropic part, how do we get? We sum up the diagonal terms, and we sum all the three diagonal terms, and that is multiplied by delta ij, and that is called the isotropic part. Okay, now, and we divide it by 3, sorry, because it's sum of all the diagonal terms divided by 3 multiplied by delta ij. Now, here, if we look at sum of all the diagonal terms is u1 prime square plus u2 prime square plus u3 prime square. So, which is equal to 2k. So, 2k divided by 3 times delta ij is the isotropic part of the Reynolds stress tensor. So that means we can write ui prime uj prime can be written as its isotropic part plus the divitoric part. So we can write uij as equal to ये प्लस होगा ये. So this is the isotropic part is this and divitoric. That means the aij, which is nothing but you can think of it as a very trivial exercise. aij is the anisotropic part of Reynolds stress tensor. And we can normalize anisotropy by writing Bij is equal to Aij divided by 2k, which means basically we write ui prime uj prime divided by 2k minus. So this is the normalized or the non-dimensional anisotropic okay. Now, why do we write it? An isotropic part, basically, now what properties do we know will this Aij tensor have? Will it be symmetric or will it be anti-symmetric or will it be general? What is Aij? Ui, uj, is it symmetric or anti-symmetric? And what is delta ij? Symmetric. So therefore Aij will also be symmetric. Okay. And then what about, what is the trace of Aij? Is 0. So therefore Aij has got only 5 independent components. Its trace will always be 0 and the trace has come in the second part, obviously.
So AIG is also 3 cross 3, diagonal terms are all 0.
No, why are they 0? So there are totally 3 diagonal terms, 3 this, but because the trace is 0, so there will be 5 independent components of Aij. We started from ui, uj at 6 components. So the 6th one is this k. So ui prime, uj prime is not independent of k. K comes from there only. Okay. So now what one can show is that only Aij part of ui prime, uj prime is effective in transporting momentum. And how do we show this? If I write rho times partial Aij by partial xj, this will be equal to rho times by partial xj and minus 2/3 d by dxj of 2/3 k delta ij. So this will become minus 2/3 d by dxi of k. See, because this is k times delta ij, so I take partial k by partial xj delta ij, and then the delta ij partial k by partial xj will become partial k by partial xi. So this is the same operation which we do. So this is what this is equal to. I'll write the first part also, rho times so now when I write the mean momentum equation, the mean momentum equation becomes rho times partial by partial xj of एक मिनट क्या लिखा है मैंने कुछ मिनट So let me go back to the mean momentum equation. The mean momentum equation will go at the start. This was dui by dt plus this, and then we had a minus d by dxj of dui dj. So in the mean momentum equation, बहुत ही गड़बड़ हो रही है. So basically what I'm trying to say here is the isotropic part can be clubbed with the pressure part, because pressure is also isotropic, so that becomes, and what we are left in the right hand side of momentum equation is only the aij by xj. The k part can be clubbed with the pressure, and this becomes a modified pressure. So now when you plug this in the mean momentum equation, then instead of pressure we will have a modified pressure, and instead of the Reynolds test term we will have aij term, and it is this aij which will affect the k will basically can be clubbed with the pressure term. So this is what we call as the modified pressure. Now we also observe one more thing. If I'm trying to give you some insights on all the velocity fluctuation terms, etc. If the flow is irrotational, that means omega I is equal to 0, the instantaneous velocity. So, and this will imply mean of omega I and omega I prime, the fluctuations will also be always 0. So if fluctuations are 0, partial ui prime by partial xj minus partial uj prime by partial xi will be 0. This follows because if the velocity it's a totally rotational flow field, then the fluctuations will be 0. We put omega is equal to 0, we get this. Now what we do is, let's multiply. So we write uj prime this will be also 0. So here actually we are not just multiplying, we are multiplying the 3 components and summing over j. But each of them will be 0, so we multiply by u1, multiply by u2, multiply by u3, and then we add them up with respect to j, so this will also be 0. Now here the first term, this becomes d by dxj of ui prime uj prime. This we are using the continuity equation, and this is equal to half d by dxi of uj prime. Right now there is no averaging, so I've taken this term on the right hand side, uj prime du prime by dxj. Because of continuity I can pull this inside, because duj prime by dxj is 0, and this one is uj prime duj prime by dxi, so it becomes half d by dxi of uj prime. Okay. Now, why am I doing this exercise? This is to show you. Now, if I take a mean, take mean of both sides. So, what we get is d by dxj of mean of ui prime uj prime is equal to partial k by partial xi. So, if that happens, then ui prime uj prime has the same effect as k times delta aj, and will be absorbed in modified P, and thus not affect mean of ui. And this is something which we had earlier. The reason I am, this is very straightforward thing, but the reason why I am doing this is, we have earlier shown that if the flow is irrotational, then turbulence cannot occur. And this is mathematically showing the same thing, that if it is irrotational, then the Reynolds stress terms take the gradient form of kinetic energy. And therefore, then they can be clubbed with the pressure term, and there will be no Reynolds stress terms as it is. In the equation, there will be nothing like this. So therefore, it just decay by, so the mean velocity will not be affected by such a velocity fluctuations. So irrotational fluctuations cannot affect the mean velocity if they are irrotational. Because the pressure, they will affect that mean pressure, because that will have a k term also, but the velocity field will stay unaffected. So last statement was, let's have a look at this is our equation, and in this equation we have this term. Now this term for irrotational fluctuations becomes dk by dxi, and therefore can be combined with the pressure term. So once you combine that with the pressure term, if you look at the overall equation, I can call this mean P plus 2 by 3k as P as, let's say, Q. Then in this equation, what will happen is the mean of P, these terms will not be able to affect the evolution of mean velocity. What will happen is, because of K, Q will change. because I've called that modified pressure as Q. So the pressure will change, and therefore, because that Q term will change because of K, P will get affected, mean P will get affected. But mean velocity, the evolution of that will not change at all. It will still follow the same equation.
If you have Q there instead of P,
Yeah.
P is still, sorry, Q is still like mean of P plus.
Yeah. So Q will change.
But that essentially is affecting my UL.
No. So that Q itself will stay the same. So whether it is that Q term, the change because of K will affect the Q term only. It will not affect the mean flow equation.
In this equation, if I have a Q state, right?
You
then
have
I just have a magnet of 1.2 density by density.
okay. No, you're not changing the Q. You're changing 2. No, so what it will do is instead of affecting Q, it will affect 1. So that basically it will become an interplay between 1 and 2. So this term gets absorbed here and it becomes like this. So what gets affected will be just this total term Q, which we are now calling as the modified pressure. The mean equations will not change.
So my contention is we have conclusively shown that 1 plus 2 is conserved.
Well, that will come, 1 plus 2's conservation will come if you take a del cross of this equation. So then you will get that this term will become 0.
So,
So this,
no, that will become 0 because goal of divergence is 0.
yeah. So
Kernel is 0.
no, so that's what I'm saying, because curl of divergence, if term 2 can be expressed as a divergence, then its role becomes just in modifying the pressure. And in fact, there was an interesting effect which we had not in this flow, it was in a laminar flow with heat transfer. With gravitational buoyancy, we were working on a problem, and where we had a Coriolis term which came in because we were looking at a rotating flow. And there, the first paper we sent, we explained the same thing. We said the velocity field is changing because of Coriolis force. One of the reviewers pointed out, but we somehow gave some explanation and he accepted it. But then it turned out that the Coriolis force in that flow, which was two-dimensional as well as incompressible, it followed an incompressible type of equation. So for that flow, the Coriolis force again became something like a divergence. So, and there then later on we were able to, because we were doing the simulations, we were able to show that the change in Coriolis force, because it got clubbed with the pressure term, only affected the pressure and did not affect the overall evolution of the velocity. Because if any change comes here in this term, then it is this term which stays the same. Probably, I think mathematically it can be shown. I have not shown it, I know, but it can be done. And I think the way to do that would be just to take the divergence, to take the curl of the equation. Then that term will also become 0. So now also one last thing before we end today. For two-dimensional flow in xy direction, where statistics is independent of x3 and the flow is statistically invariant under reflection about x3. Now, in such a flow, on the z axis, what you will find is this will lead to u3 is equal to minus u3, and this will imply u3 is equal to 0 at x3 is equal to 0, and also because of this you will also get u1 prime u3 prime and u2 prime u3 prime will be 0 at x3 is equal to 0. This comes by taking a reflection if about the z-axis, if this is the z-axis, then u3 and minus u3, they will be equal at the axis. So at axis, we get u3 and the stress, the three components wherever the third axis comes, because we are in a two-dimensional flow and because the flow is invariant under reflection about x3, this will become 0. Now, because the flow is two-dimensional, these statistics will not depend on x3. So that means u3 will be 0 not only at x3 is equal to 0, but all values of x3. And similarly, these will be 0 not only at x3 is equal to 0, but at all values of x3. So therefore, in such a flow, in a statistically two-dimensional flow, so this will imply, and because statistics do not depend on x3, we will have mean of u3 is equal to 0 and u1 prime u3 prime and u2 prime u3 prime, they will be 0 for all x, y, z. And in this case, the Reynolds stress tensor will look like u1 prime square, u2 prime square, so in a two-dimensional flow, the Reynolds stress tensor, if the flow is in an average sense two-dimensional, it looks like u1 prime square, u1 prime, u2 prime 0, u1 prime, u2 prime, u2 prime. u3 prime square, mind you, will not be 0 because while u3, there's a single vector is 0, but if it's a product, then if u3 prime here is there, then in the other side also the square will not be 0. So this is how the Reynolds stress tensor will look like. Now tomorrow's class, we will continue from here. I will start with the scalar equation and we will look at the eddy viscosity hypothesis. What is the eddy viscosity hypothesis? And then we will move on to other modeling. We have already seen what is eddy viscosity, but you will realize the way we have done it here using this Aij, we will be able to do it in a very tensorally compact way. And I will try to explain what is happening in terms of the components and the mathematical meaning of each of these. Yeah, sure. Or now this particular part is from Pope's book, what I am covering now. This is one of the earlier chapters and then I will move on to chapter 9 and 10. This part is, I think, somewhere at the start. So I'm picking out parts which are relevant, and at least most of the things we are doing now, you should be able to relate to it, because all these derivations, in fact, we have done earlier. So I don't want to make it more complex towards the end of the course. But what you have to be very familiar with is how to expand the equations and all. We have done that in the exam also earlier, that you should be able to do.